Hello, my name is Bryson, and I'll be starting off this presentation on our 496 project called the Sensor-Based Replicator. On this slide, we'll be discussing the objective. The objective is to create a device that can scan an object and create a 3D printable file based on that scan. That scan will be obtained through the sensor that is in the device, and it shall also contain the apparatus for the sensor and any sort of motion-oriented devices. Some additional objectives we've designated is to make the device fully eligible for patent, add material recognition, and add a secondary sensing method for verification. The last two additional objectives were specified by the coding subsystem. On this slide, we have our subsystem overview. On the right hand side, we have a figure of what our device will look like. This is our initial plan on how we're going to design everything. And how we'll be designing it is split up into three subsystems. One subsystem is the coding. They're in charge of data processing and filtering the data. Research subsystem is in charge of sensor research and sensor implementation. And physical implementation subsystem is in charge of motor controls and feedback designs. On this slide, I will be discussing the coding subsystem progression. The topics we have chosen to look into this semester has changed to computer vision and machine learning applications. We have decided to put the progression of the data processing on hold till the sensor research is closer to completion. For machine learning, we will be looking into implementing some sort of material identification, and for computer vision, we will be using it as a secondary verification method. Currently, we are looking into using photometric analysis as the secondary method of scanning, and we will be using OpenCV with Python to run it. Currently, we are also researching another alternative method. One alternative method to Python and OpenCV is MATLAB. MATLAB has a toolbox that can help us greatly, but that toolbox is over $1,000 and is hence over budget.
Throughout our project, we initially have chosen the Arduino HC-SR04 component, and with the schematic on the left represents the layout of the components for the HC-SR04 Arduino ultrasonic sound sensor. And throughout our semester, when we conducted our experiment, we came to the realization that the sound sensor was not producing its accuracy based on its specifications, and we came out to a difference of 3 centimeters of inaccuracy data collection. Therefore, as we continued to do research, we found another schematic that contained an upgrade for the HC-SR04 ultrasonic sound sensor with a few minor adjustments where a couple resistors were changed, along with the change of the microcontroller, because the original microcontroller was a Chinese OPT U controller, and the new schematic shows them to use a tiny 24 SOIC microcontroller. And as we input a specific portion on the schematic into PSpice, it generated a bandpass filter where the original bandpass filter was centered at 18 kilohertz, which is not up to the specifications of the HC-SR04, where it was supposed to be centered at 40 kilohertz. And this could be due to the reason, or this could show the reason why we were getting inaccurate readings based off the original schematic layout and component values. So our next step will be to change specific resistors along with the microcontroller in order to have the bandpass filter centered at 40 kilohertz where it originally needed to be, and conduct further more experiments and to see if that will change the accuracy within our ultrasonic sound sensor.
Throughout the semester, we were using the ultrasonic sensor HCSR04 as our base model. As you can see on the slide, the ultrasonic sensor looks generic in design. We then asked ourselves if there are any improvements that we could do to the sensor to better the performance while keeping the cost reasonable. So we come up with a few improvements that we think could possibly make it better. We thought about switching out the transducer to make a better one, find a way to increase the sensor's transmitting and reading frequency, or change some resistors around. So if we decide to change the transducers, we must consider the different types of transducers. There are two different types of transducers we could use, which is a straight beam transducer or dual element transducer. The difference between the two is that the straight beam transducer uses one element to transmit and receive ultrasonic pulses, while a dual element transducer uses two elements. The sensor we have is a dual element transducer. Our next option of improving the sensor is by having the sensor sending out ultrasonic pulses in higher frequencies and changing out the resistors to change the reading sensitivity of the receiver. We believe that if we increase the frequency the transmitter sends out, the receiver will be able to have better readings. Since we are using a schematic that uses a dual element transducer, we are going to find a different type of dual element transducer that would perform better than the one we have. We then change the resistor values of the board to change the sensitivity of the receiver. There were different types of transducers that we looked up, but majority of those transducers required contact to the surface of the object for them to work, and the cost of buying a transducer that would work for our application would be pricey. By changing the resistor values, we will be able to filter out unwanted noise. This way is cheaper compared to changing out the transducers.
Hi, my name is Chad, and I'm going to be talking about the hardware section of the project. And essentially, the breakdown of it is going to go with the block diagram implementation and design, the operation of our design. We're going to be talking about the rotational drive platform and the vertical axis drive. To start out with the block diagram, we chose a unity feedback loop, which is essentially the diagram displayed to the right. And the input to the system is our microcontroller. And the forward path consists of a plant cascaded with a compensator. So it's software driven and it drives the motor controller. And the output to the system is the stepper motor. And in the feedback loop, you have the rotary encoder, which goes back to the software. The operation of our design. So the microcontroller, like I said, is the stimulus to the system, and it's going to be driven by a software which is we're using is Arduino. And what it does is it corrects the motor controllers, and it receives feedback from the rotary encoder. The motor controllers controls the amount of rotations of the stepper motors that we're going to use. So essentially we're using two stepper motors, therefore we have two motor controllers. The two stepper motors that we're using is one is for the turntable in which the object is being scanned on, and the second one is used for the vertical axis in which the sensor is going up and down on. So with two stepper motors, we also have two rotary encoders in which they will track the amount of rotations in which the stepper motors rotate. So if you look to our pictures to the rightmost picture shows the axis which is mounted into the stepper motor, which is going to allow the sensor to move up and down in the vertical direction. And shown below are the motor controllers that control the stepper motor's rotation.
Up next is our rotational drive platform. The components involved are the stepper motor, motor controller, drive gear, rotational platform, a rotary encoder, and the design of this build is to have the stepper motor connect to a drive gear, and that is connected to the drive platform, which is connected with another drive gear, and that would in turn have the most accuracy for scanning, and it would have to have a 1-to-1 ratio. The rotational encoder is actually connected straight to the stepper motor, and this is so that the system has memory, and so it would actually know how many steps it took, as well as how many steps it needs for a full rotation and how many steps in order to figure out how many steps it needs in order to stop. Up next is our vertical axis drive platform. The parts that are in our vertical axis drive is the stepper motor, motor controller, rotary encoder, coupler, and gear drive shaft. The stepper motor is mounted to a platform, and then the coupler is connected straight to the stepper motor gear drive shaft, and then from there the gear drive shaft is connected straight through the coupler, and that would in turn have a platform rising up and down the gear drive shaft. And from there our sensor would be placed on top, and it would actually go a one full rotation, and that's one step vertical, as well as it will also have a rotary encoder connected to the gear drive shaft in order to have memory in our system. It is important to have memory in our system so that we would have less errors, and we would actually have more accuracy due to the fact that we have memory in our system, so that we can track how many steps it took, as well as how far is it away from the top, as well as from the bottom.